Okay, at the end of class last time, we learned canonical form. Remember that? What the canonical form is? And what a min-term is. We can recognize a min-term in a canonical form. In a canonical form. And then, and we can either have or by duality, we can have and or. Actually, we usually think of it the other way around. We usually work with and or circuits. And then the one that's a little trickier to work with because we're used to addition and multiplication being a certain way compared to and or, it's usually harder to do or and circuits because of our experience with algebraic expressions with addition and multiplication. But at any rate, what we're going to do today now is we're going to do this optimization problem that we described last time. Now, so let me ask you a question. Is the optimization that we are doing now a space-time trade-off optimization, yes or no? No. Correct, it's not. Because what is the computation time for all two-level networks?
2 gate delays.
2 gate delays. So we're just taking a look at space. We can decrease the space with no change in the time, with no increase in the time, because this processing time is going to be 2 gate delays. So now here's how we do it. Now we have another little useful tool in our toolkit. It's called our Karnaugh map. It's named after Karnaugh, who developed the technique. And basically what a Karnaugh map is just another way to draw a truth table. A Karnaugh map is a truth table drawn a certain way, right? And it's drawn in such a way as to facilitate this optimization that we want to make. Now, to see how we make a Karnaugh map, we first have to understand what we mean by the distance between two min-terms. So let's suppose that we have a function of 3 variables, a, b, and c. So a, b, and c are the input. Okay, so we have a 3-input circuit. We're going to be talking about 3-input circuits today. And so let's say that those variables are a, b, and c. Now what does it say here is the definition of the distance between two min-terms. So let me ask you a question. A prime, b, c. Is this a min-term, yes or no?
Yes.
It is. We know this now. This is a min-term, okay? Now what about the min-term a, b prime, c? This is a min-term too. Also, right? And what's the distance between this min-term and this min-term?
2.
It's 2. Now, does everybody see why? The distance between two min-terms is the number of places in which they differ. They differ here in the A because this is a prime and this is not. And they differ here in B because this is not a prime and this is. So the distance between these is 2. Does everybody see that that's how to calculate the distance between, or what the distance between two min-terms is? All right? And so, suppose we have A prime, B, C. Can you give me a min-term that has distance 1 from this one? ABC is a good example. So the distance between these two min-terms is 1. Why is that? It's because they only differ in the A. There's a prime here and there's not a prime here. Is everybody clear on this? So here distance equals 1. The distance between them. Right? Now, and here's what Karnaugh did when he developed this little technique with the maps. It's a great little visualization tool for small problems. As long as you don't have too many variables, too many input variables. Okay? And so, oh, by the way, these two min-terms are adjacent. So that's what we mean by adjacent. We mean the distance is 1. Are you with me? So these two min-terms are adjacent. These two min-terms are not adjacent, right? Now look, how do we normally order a truth table? If we have a truth table and there's some output is here and we have this A, B, C, how did we always construct the truth table? What order did we did it? We would, 0, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, right? Now tell me, what's the distance? Are these two adjacent?
Yeah.
Yes, they are, because they differ just by 1 in the C place, right? What about this?
No.
They're not adjacent,
2 apart.
because the distance between this is 2. What's the distance between this?
1.
1. Distance between this?
3.
3, right? They differ in all 3 places. 1, 1. All right? So here's what a Karnaugh map is. A Karnaugh map is, with 3 variables, has 8 cells. And they are drawn in such a way that the cells that are physically adjacent to each other are adjacent with distance 1. So what has to be next to what? This one would have to be next to this one.
And then the following one.
And then this one would have to be next to this one.
Right.
You see what I mean? And so, are you with me? So the whole thing is that, and check it out, you guys. Here's what a Karnaugh map looks like with 3 variables. Now look at part A of figure 10.26 here. Look, this is so clever. Look, you see here on the left-hand side, we have the row represents A. So the top row is where A is 0, and the bottom row is where A is 1. Are you with me? And then on the top, we have the columns. But the columns, we have BC. But now but the first column is when BC is 0, 0. The second column is when BC is 0, 1. Now, why isn't this column 1, 0? Why isn't it like the truth table, 0, 0, 0, 1, 1, 0, 1, 1? Because the adjacent, they have to differ by 1. Right? So look at the pattern. So the pattern here is BC is 0, 0, 0, 1, 1, 1, 1, 0. Now, is everybody, and you see why? I mean, you see because we want them to differ by 1. Is everybody with me on this? All right? Okay, and now you understand that this cell, okay, so I'm pointing to the second cell in the top row. What entry in the truth table would that be? ABC equals what? 0, 0, 1. The third cell in the top row represents ABC 0, 1, 1. And what goes in here is just what would go in the truth table, here. Because this is just the truth table. Are you with me? Now, check this out. It's useful to visualize this truth table kind of like a Venn diagram. Right? And if we keep in mind that these columns are the values of BC with the pattern 0, 0, 0, 1, 1, 1, 1, 0, and the rows are A, with the top row being A equals 0 and the bottom row being A equals 1, then we can talk about regions. So part B of the figures shows the B equals 1 region. So now, where is the B equals 1 region? It's those 2 columns where B is 1. So it's the right half. So you see that shaded there? So the right half is the B equals 1 region. And what about the C equals 0 region? Well, that's what? Where is C0? The left column and the right column. Does everybody see that? And okay, so let me ask you, where is the C equals 1 region? The middle 2. Where is the A equals 1 region? Bottom row. Is everybody with me? So you can see there's regions associated with a particular value of a variable. Okay? Now, what we're going to do next is we're going to see how this Karnaugh map is used to give us the minimum circuit. So the first example we're going to look at is in figure 10.27, and what we're going to do is we're going to write the function that we want to minimize is the function x of ABC is A prime BC or A prime B C prime. All right? Now, I have a question for you. This expression in part A of the figure, A prime BC or A prime B C prime, is that a canonical expression, yes or no? Yes, it is a canonical expression. And that means that the truth table for this is going to have how many ones in it? Two. There's going to, and the rest of them are going to be what? 0. Is everybody with me on that? Mm-hmm. So do you see then that the Karnaugh map in part A of the figure has, and so what values of A, B, and C will have a value of 1? A, B, C equals what? 0, 1, 1. And so that's what? First row, third column. Are you with me? And what's the other one? 0, 1, 0. And so that's first row, fourth column. And so you see there's a 1 there and a 1 there and everything else is 0. Now does everybody see that this is just a truth table? Now here comes the first big thing that we're going to do. From now on, when you have a Karnaugh map, don't write down the zeros. Leave it blank. Are you with me? Standard practice when we do analysis or when we do design, minimization design, is to omit the zeros in a Karnaugh map, because otherwise it gets way too cluttered, because we're going to have some more lines going through there, okay? So do you see then that in part B of the figure we have the ones there and the others are blank. So if it's blank, we assume that it's 0. Now, watch this. Let's take a look at this. Let's take a look at that expression. We have A prime BC. Here we have A prime BC or A prime B C prime, right? Mm-hmm. Now, you guys, look, these differ by how much? Each one of these differs by how, what's the distance between them? 1. The distance between them is 1. Do you see an interesting algebraic manipulation?
You can distribute out the A prime B.
Yes, we can use distributivity. So this equals, by distributivity, this equals by distributivity A prime B, and then what do we have? The one place where they differ. And so what do we have here? C or C prime. Are you with me? This is C or C prime. Yeah? But what do we know about C or C prime?
1.
That's 1. Which law is that? By the complement law, that's A prime, and B, and 1. But then what do we know about and 1? That's just the identity. So this is what? Equals by identity. Identity A prime B. But now look, you guys.
It's not a midterm.
It's not a min-term, but I ask you a question. How many gates? Let's take a look. Let's take a look at how many gates this is. And then let's take a look at how many gates this is. Okay? So if I asked you, a couple days ago, if I gave you this function, I said, draw the gates, how many gates would you have to draw? How many? And what gates are they? And how many inputs with each AND? And how many AND gates? 2. So this is what? 2, 3 input,
And gates.
and
1 or.
And 1, how many inputs?
2 input or gate.
And 1, 2 input, or.
Or 3 NAND gates.
Or 3 NAND gates. Is everybody with me on this? And by the way, the primes will just, the inverters will just, they're small little things. We won't count them, just as an approximation. All right? But now what is this?
That's one
One,
AND gate.
how many inputs?
Two input.
Yeah, and this is just one 2 input AND gate. All right? And it does the same. Actually, in this particular example, that won't always work out like this simple. But not only have we minimized the space, we've also, because what's the gate delay here?
One.
There's just one gate. We've also minimized
The gate.
the gate, yeah, the time. We've minimized the space and the time. So that's a little unusual. I mean, it doesn't work out like this. Frequently the time stays the same, right? But we minimize the space. So does everybody see how that works? I mean, but now look, the neat thing about a Karnaugh map is that you don't have to do this. Because what happens is, what a Karnaugh map allows you to do is it allows you to do this computation visually on the Karnaugh map. Because look, you guys, because these ones are next to each other, we can circle them with an oval. And then take a look at what region this is. Now, first of all, what row are these two ones in? Yeah, the A equals 0. So therefore, these ones are, if I ask you, what is the A prime region? What region would that be? Yeah, the A equals 0. So that would be the top row. The top row. And then what region, and what region are the what region is the rightmost?
B equals 1.
It's the B equals 1 region. Do you see what I'm saying? So it's A prime B. And you just look at the Karnaugh map and say, oh, that's A prime B. See? You don't have to do this, 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 this. You just look at it and interpret the regions. You can see that it's where A is 0 and it's where B is 1. If you take a look at the B values, it's where A is 0 and where B is 1. So you can just read it right off the Karnaugh map. You don't have to do all that algebra, Boolean algebra. Is everybody with me on this? Okay, let me ask you another question here. What cell is adjacent to this lower right-hand one? This lower right-hand cell is for A equals what? 1. Well, it's for ABC being what? It's for ABC, sorry. Yeah, that's what I meant to say. The term is ABC prime. Now, ABC prime is a distance 1 from ABC, which is to its left, and it's also next to what?
A prime, B, C prime.
A prime, B, C. But there's another one that it's next to. The lower right-hand cell is which one? A.
B, C prime.
Doesn't it wrap
A, B, C. Yeah. It's A, B, C prime. So what is the distance 1 here? Which cells are a distance 1 from here? You said the one to the left is which?
ABC.
It's A, B, C, so it's adjacent to this. It's also adjacent to the one above it, which is what? A prime, B, C prime. A prime, B, C prime. But it's also adjacent to what?
A, B prime, C prime.
A, B prime, C prime. A, B prime, C prime. Are you with me? This is a distance of 1 from this, this, and this. But which cell is this?
Bottom left.
It's the bottom left. So, oh, B, A, yeah, sorry, A, B prime, C prime. Thanks. Is everybody with me on this? So look, that's the one. So basically what we have is what's called, what I like to call this, like the Pac-Man effect. You know that old 60s video game, Pac-Man? And the little thing goes bloop, 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 out one side and bloop, 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 it comes down on the other side. So it wraps around like this little Pac-Man effect. Okay? So what you have to keep in mind is, so suppose we had, look, so here in figure 10.28, we have the function A, B prime, C prime, or A, B, C prime. Well, A, B prime, C prime, that's 1, we have to look at which cell. 1, 0, 0, yeah? So that's the 1, 0, 0. That's the lower left corner. Are you with me? And then this A, B, C prime, that's the what?
1, 1, 0.
The lower right corner. But now when you draw the oval, you have to draw it like with the Pac-Man thing. Now it looks like a basketball court. Yeah, there's the hoop. There's the other hoop. And if it's a three-pointer if it's outside the circle. Right? But now, do you see that this circle right away? You don't have to do any algebra. Right away, how can you determine which and what that and term is? Well, it's the bottom row. Yeah. So that's going to be A, and then which columns? The outermost. So the outermost. So if you look at the outermost, the left column is 0, 0. The right column is 1, 0. So what's the same there? C being 0. So that's AC prime. So here's the A region. That's the bottom row. The C region, the C prime region is that, and so it's like the intersection of those. But you can just see, or you can just tell from the digits, from the ones and zeros. Is everybody clear on how to do that? All right. Now, the examples that we've done so far have had just 2 terms. But what if you have 3 terms? All right. So here's the next one. What if we have 3 min terms? What if the truth table has 3 elements in it? So now, figure 10.29 has a function, and now what is the canonical expression for this function? There's 3 ones in it. There are ones in the third column, and there's also ones in the right half of the bottom row. Right? So there's 3 ones. So now, just looking at the values of A, B, and C, the first row, that's what? 0. That's A prime. This one is A prime BC. Are you with me? Mm-hmm. So that's A prime BC. That's this one. And then the one just below that is what? ABC. So that's this one, the second one. And then the one to the right of that in the bottom row is ABC prime. Are you with me? Now, you guys, watch this. Suppose I gave this to you. This is where the Karnaugh map really works well. Suppose I ask you to minimize this algebraically. Do you see how to use Boolean algebra to get from here, from A prime BC or ABC or ABC prime? Do you see Boolean algebraically how to get from here to here? Guess what you would have to do? You would have to pull a rabbit out of the hat. Do you see what rabbit you'd have to pull out of the hat? Look. What would you have to do?
You could pull AB out of the right 2 terms.
Yeah, what about the middle term? You would have to duplicate it.
Yeah.
Good call.
Yeah.
And how could you duplicate it? Idempotency. You'd have to use idempotency to temporarily make it more complicated. So you'd actually have to do A prime BC or ABC or ABC prime. So this would and then by idempotency, this would be A prime BC or ABC or ABC again or what?
ABC prime.
ABC prime. And here you would have to use what? Distributivity twice on this pair and then on this pair.
Right.
Are you with me? So distributivity twice. Distributivity twice. Okay, and so this would be, so what would you pull out here?
A or A prime?
A prime, let's do it in order. So anyway, so A prime or A and what? BC or, and now what would you pull out here?
AB and
AB, yes, this would be AB and C or C prime. And then this would equal by, let's do 2 steps in one.
Complement and identity.
Complement and identity.
Twice.
Complement and whoops.
Identity.
and ident twice. So this would be what? BC or AB, right? But now look, you guys, watch this. The way you do this in a Karnaugh, so it would take all that algebra. But with a Karnaugh map, what you do is we see that there is a 1 here and a 1 here, and those are next to each other, so we can draw an oval around them, right? We can circle them. And it's so even though this one is circled, it's okay to group it again. And in fact, the fact that this, you see, because if we can circle the bottom two here as in part B of the figure. Now, in part A of the figure, that represents the fact that A prime BC or ABC equals BC. Are you with me? And then part B of the figure represents the fact that ABC or ABC prime equals AB. Right? So, in the Karnaugh map, you just put the ones here, the one here, the one here. You draw the oval around that column. You draw the oval between those two in the bottom, and it's okay to reuse this one. And the fact that you're reusing this one corresponds to algebraically to doing what? Pulling this rabbit out of the hat, actually. Are you with me? And so, what you do, so when you have more than one grouping, what you have to do is you have to cover all the ones and none of the zeros by grouping. And once you get all the ones covered and none of the zeros covered by grouping, and by the way, you can only group 2 or 4 or 8. You can't group like 3 or 7. You see what I mean? The ovals, because the oval has to correspond to a region, each grouping has to correspond to one of the regions of the table. Are you with me on that? You see what it takes a little geometric, a little Venn diagram kind of a.
You said like 2 or 4 or 8.
Yeah, it has to be. Yeah, you can only group, you can't group, or 1. Actually, there might be a situation where you have to just group 1. Even that can happen.
So the powers of 2?
Yeah, yeah. Because they are powers of 2 because the regions of the table have to correspond to an and. You see what I mean? So if the A equals 0, 1, well, that's all the ones where A is not 0, and that's going to be a power of 2 number of cells. You see what I mean?
Well, like they just get 2 cells, they have to be adjacent.
Well, yeah, they have to be adjacent. You are grouping ones that are adjacent, yeah. And the reason they have to be, that's the genius of Karnaugh, this is constructed so that they are adjacent. But if they are adjacent, then that's equivalent to doing this algebraically. See how neat that is? Is everybody with me? So look, so what you do is, and you just OR each group, right? So what is that third column? What does that third column represent? Well, that's the BC equals 1, 1 column, right? So that's just what? BC, right? This column right here, so here, this column right here is BC, and then what is this little group right here? That's row A, right? And the right 2 columns are where B is 1, so that's AB. So this is BC or AB. Boom, you got it. You don't have to do all of this stuff. Is that neat? Now, here's another thing. Frequently, I'll give you a homework assignment, and instead of drawing the table, we're going to use that sigma notation. Now, think about the sigma notation. What is that sigma notation?
It's or.
It's, it's sigma, parentheses, and then
All the things inside it.
those, what are those numbers? Those are decimal numbers inside, right?
Right.
So, and what did those decimal numbers correspond to?
Number.
The corresponding, the midterms, but the binary, the binary, considering A, B, C to be like a binary number, where A is the most significant bit.
Right.
Are you with me?
Right.
So tell me, if our Karnaugh map is shaped like this, 0, 0, 0, where is 0?
Top left corner.
Where is 1?
The 7th box?
Wasn't the one right to that?
It's the one to the, just to the right of it, right? This is 0, 0, 0.
One, so they meant
This is
1.
0, 0, 1. But now where's the next one?
2 is on the far right.
It's the one over to the far. And then where is 0, 1, 1? That's just to the what? To the left of that. Now, does everybody see that pattern? Here's the picture. Figure 10.30. This is a Karnaugh map with the cells numbered the same way we did with the sigma notation. Are you with me? Is everybody clear? So now, let's do this. Now let's do it. Now don't peek. If you have the slides, do me a favor and don't peek. So I can see what's coming ahead, but let's just try to do this on our own. Those of you, that goes for you guys out there and watching this recorded too in video land. All right, let's try to do. Suppose I ask you to minimize sigma 0, 1, or x of ABC equals sigma 0, 1, 5, 7. X of ABC equals sigma of 0, 1, 5, 7. All right, now let's see if we can do this. First of all, what I want you to do in your notes is draw the Karnaugh map with the 1s in it and blanks where the 0s go. So now, can you do that? Do you see how to do that? Mm-hmm. So do it on your... So this is A, this is BC, and so this is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. And so now how does this numbering go? It's 0, 1, 2, 3, 4, 5, 6, 7. Right? So where do the 1s go? 0, 1, 2, 3, 4, 5, 6, 7. So is this what you got? Mm-hmm. That's what you should have gotten, right? Okay, so now you guys, tell me, what's one obvious column that we could group? I know, I was trying to lead you down the incorrect path. But we could do the column.
Right.
I mean, you could say, oh, these two, because what term would that be?
That would be B prime C.
That would be B prime C. So we could do this column and have that be B prime C. Then we could do what?
A prime, B prime, C prime.
A prime. These two would be A prime.
Oh, you want to do, okay.
Yeah, these two
That would be A prime, B prime.
would be A prime, B prime. Yeah, so the middle, what did we say the column was? B prime C? So B prime C, or, and then what was this one?
A prime, B prime.
A prime, B prime. And then we could cover what?
The third one.
These, like this, and what would that be? A, that's the A row, and then it's when C is 1. So this would be AC. Or AC. But, look, why is this not minimum? Because, as you pointed out, we should not have done what?
B prime C.
We should not have done B prime C. So even though this is mathematically correct and the circuit would perform correctly, it's not minimum. So let's take a look at figure 10.31, and we see that using that column was the result of a bad strategy because we can cover them all with just these two, which is A prime, B prime, or AC. So that's the part C of figure 10.31 is the correct minimization. Does everybody see how to do these? You're going to have a bunch of them for your next assignment. Are we good?
I was just looking at how to get rid of the B prime C.
Oh, you mean like algebraically?
Yeah.
Yeah, isn't that interesting? How would you? Yeah,
I think
that's,
that'd be another rabbit you'd have to pull out.
yeah, I think you, yeah. Oh, that's an interesting question. Yeah, how would you get, because this one, yeah. This is the same function as just getting rid of that. Wow. That might be kind of hard. Well, I mean, I'm sure you could do it. Check this one out. Let's do x of ABC equals 02467. X of ABC equals sigma what did I say? 02467. Sigma 02467. Try that. Try that on your in your notes. I bet I'm gonna.
Yeah, nope.
I think. Do you think? I think I might. I think I might have you on this one.
It's C prime.
Hold on. Oh shoot. You got it. Okay, so this is A 01, B C 00 01 11 0. So what is 0? So 0 1 2 3 4 5 6 7. Is this what you got for the Karnaugh map before we group? Now, the question though is, how did you minimize? First of all, what about this little one right here?
That's ABC.
I got you. Oh, it is ABC.
Yeah,
This is ABC. So did you have ABC in your result?
I did.
I did get you.
That would make it, oh, you're saying because that would make it,
What?
so do you want me to do C or,
Well, look,
it's C prime or something?
huh? Well, you got to cover them all, but don't, oh yeah, look. Don't cover this
By itself?
like this.
Ever?
Ever. Well, hardly ever. You guys know HMS Pinafore?
Yeah.
Anyway.
Yeah, you can just do it twice. So you're covering,
Look,
Covering the
there's no reason to look. Do you understand, if we go back to the previous examples, do you understand that the bigger the region, the what?
the less,
The fewer inputs to the, each region represents a what? Each covered region represents a what?
a letter, or
No. In the circuit. In the circuit, each group
a gate.
represents a gate.
Right.
The bigger the group, the what? No.
Smaller the input?
The fewer the number of inputs to that gate. Are you with me?
Yeah.
So
Okay,
that
so-
saves space. Are you with me?
So it'd be,
So if you just covered this by itself, what kind of a gate would that be?
it'd be a two,
It'd be-
two
no.
level.
No. What kind of a gate?
It'd be a
would-
three-input and.
If this was just by itself, it would be a 3-input and. But on the other hand, if we cover it like this, what is it?
Then it's a 2-input.
It's a 2-input and. In fact, what term does this represent? A what?
B, AB.
AB.
Yeah,
So this one by itself is ABC, but this one is just AB.
right.
So why use a 3-input input AND when you can use a 2-input AND.
Right.
Are you with me? Now, is everybody clear on that? This one this one is AB because it's in row A. Okay, are you with me on that? It's row A, and then it's it's the two rightmost columns. So do you see that the two rightmost columns are the columns where B is 1? Yeah, that was a good question. This is what's tricky about using Karnaugh maps. So because it's the two columns where B equals 1, that's why it's AB. So this term, this grouping represents the conjunction AB. Because it's row A and region, it's the region where A is 1 and where B is 1, because the two right columns are where B is 1.
Right.
Well, when is it C prime then?
Well, it doesn't include C. It doesn't include C because this is the ABC and this is the ABC prime, but the C or C prime can be factored out, which is B1. You see what I mean? So the C, I mean algebraically, are you with me?
Yeah.
So because the C is 1 here and it's 0 here, but that means we don't need it. Yeah, good. All right. So this, yeah. All right. Now, so does everybody see? That's why you got to make the grouping as big as possible. Now, and how about this? Shall we group this column?
No,
Why not?
because there's an entire C prime region covered.
Yeah, it would be a mistake. Did you do it like this? So, a lot of people do it this. They do this column, and then this column. Now, if we did it that way, I don't think I want to mess up the board that way because it's incorrect. But if we did it this way and this way and this way, what would we have? Now, what did we say this one was? This one was what? A. This one is A what? This one down here, what did we say this one was?
AB.
This is AB. And then if we did OR, and then if we did these two, what would that be? A, no, it doesn't have, these two would not have A in it. Oh, I'm sorry, I thought you said A. B prime, C prime, and then this would be what?
BC prime.
BC prime, or BC prime. But that would be incorrect. That would be an incorrect minimization. Because what can you do? You can do you could do the Pac-Man on the top and the Pac-Man on the bottom, but that would still be,
The same thing.
are you with me? If you did the Pac-Man on the top here and the Pac-Man on the bottom here, that would still be the same number of gates. So instead of doing that, what do?
Double Pac-Man.
Yeah, do 4, group 4, and group it like this. Does everybody see how that works? So you group it like that, and now what is this one? So we still have, this one is still AB, right?
We did algebraically.
So this is AB, but now, what did you say this region was?
C prime.
The C prime region, or C prime. And now, how many gates is this? Now let's count the gates.
2 gates.
Here, let's count the gates. No, it's not. Oh, yes, it is. So what is this AB? It's 1,
2 input.
1, 2 input AND, so that's 1, 2 input AND,
And 1 2 input OR.
and just one, because this doesn't have an AND, it's 1, 2 input OR. Now, what's the gate delay? And you could draw this circuit if you wanted to. Now, does everybody see that this is a gate delay of 2? Because it's the longest number of gates between the input and the output. Is everybody with me on this? So here it is. See? And so here is an incorrect minimization. I tried to lead you down the path of incorrectness, just to make a point. Here's an incorrect. And that's B prime C or BC prime or AB. But here is the correct minimization in part B of figure 10.32. Are you with me? Yeah, question?
If you had, like, for example, the second column and the fourth column,
Oh, good, yeah, let's,
then you'd have to use
that's a,
exclusive OR gates.
yeah, but look, we don't, this is all done with and/or.
Okay.
We're just assuming and/or.
Right.
And you're right, yeah,
Then you could just do like these.
yeah. There are other methods, and some of them are kind of ad hoc, and you could say, well, if you could use exclusive or, then that's a whole different ballgame. So we're just going to assume and/or, because that can be done with NAND. And NAND is, they make those things out of NAND gates anyway. So internally,
They make exclusive ORs out of AND?
they make everything, look, we're going to end on this. I forgot, I don't think I emphasized this very well last time. Okay, let's go back to figure 10.22. And in 10.22b, so what we know is that every combinational circuit can be reduced down to a two-level and/or.
Right.
And we know that a two-level and/or can be built with only NAND gates, right? And furthermore, in figure 10.23, we also know that you can actually construct
Inverters.
an inverter from a NAND gate. Do you realize what that means? What that means is that an entire computer, if you were stuck on a desert island and you had only NAND gates, you could build an entire computer with just NAND gates, because any function that you want to construct can be done with two-level NAND, which gives you the OR, right?
Yeah.
It gives you the AND and the OR. And furthermore, an inverter can just be made with an AND. So that means, so there's this phrase. It's called the ubiquitous NAND. Uh-oh. I'm not, how do you spell ubiquitous? T-O-U-S? Ubiquitous NAND. And furthermore, I don't think it's a coincidence. Remember I told you that the fewest number of transistors, it takes fewer transistors to make a NAND than it takes to make an AND. In fact, the way they do it internally is they make a NAND and then they put an inverter on and they turn it into an AND. So, not only is it practical to have everything be done in terms of a NAND, but also theoretically, you can make anything with a NAND. See? And in fact, I'll tell you that there are some logic systems. You know how in formal methods we started, do you remember the very first axiom that we started with in formal methods? It was equivalence, associativity, and blah, blah, blah. And then we did, after we did equivalence, we introduced, do we do disjunction first?
Before conjunction?
Yeah,
Absolutely.
I think we did disjunction first, and then we had what rule? The golden rule that introduced conjunction, and then we had a definition of implication, and so on and so on and so on. There are actually, it's actually possible to construct an axiomatic system that has only one operator, NAND. And then you can define everything just in terms of NAND. And some people actually do it that way. You see what I mean?
Yeah.
Because with NAND, it corresponds to this. From a digital circuit design perspective, you can construct any circuit with a NAND. Well, you can actually define all other operators in the propositional calculus with just the NAND. So we started with the equivales because it's an equational system. So we emphasize that. But in hardware, actually, it makes sense to consider the NAND to be the apps. And we didn't. Our axiomatic system didn't do that. Our axiomatic system had had a set of 10, dual axioms. Axioms and their duals. So, but still, it's an interesting perspective to know that everything can be done with just the NAND. Oh, and by the way, by duality, guess what else is true? Everything can be done with just the what?
NOR.
Just with the NOR. Mm-hmm. So you could take either one to be, and then define everything else in terms of just NOR. Because you can also make an inverter with a NOR.
Yeah.
Okay, are we good? Is this fascinating stuff or what?
Yeah.
I think it's really cool. All right, see you on Thursday.